Hello, Mr. Fritz here, and I'd like to talk to you about functions. Well, let's start off by talking about what is a function. A function is called a rule which relates an input to output values, or I should say relates input values to output values. There must be only one output for each input. And what this is really important, and this is kind of at the core of what a function is. We can think of a function as a machine. We put stuff into a machine and something comes out of a machine. If there's some sort of relationship, typically when you see functions, you're seeing equations, you're seeing graphs, you're seeing tables, but really we can harness this whole idea that there's only one output for each input. What that means is if I put something into my machine, only one thing should come out of that thing. Think about it like this. If I had a vending machine and I had all kinds of snacks inside my vending machine and I pressed the code A3, there should only be one thing that comes out of this, right? If I pressed A3 and I didn't know if it was going to be like Doritos or Oreos that came out, that's not a very good vending machine. Vending machine is a great example of a function because when you press one input, only one thing, one snack comes out of this thing. Only one. Okay, so let's talk about how to represent functions. We have four different ways shown here. We can use what's called a map, and a map is a cool way to represent a function because it takes a series of inputs, and what it does is it maps them to outputs. And the process of mapping an input to an output is pointing. So we would say that 0 maps to some output. I'm just going to kind of make it up. Let's say it maps to 1. And let me throw these other numbers down, 5, 9, and 13. We could say then that the input of 1 in this function maps to 5, the input of 2 maps to 9, the input of 3 maps to 13. Basically, it's like saying this input does some stuff and then makes its way over to an output. It maps to an output. You could do the same thing with a table. We could have 0, 1, 2, 3 for inputs. I could have 1, 5, 5, 6 for my outputs. Notice here that I have this repeated outputs. That's okay, but I have different inputs, so that's good. I could say that I have a graph that is a function. It could look something like this. Here's a good graph. This is like a cubic function. This is a function. One thing that you're going to start to hear, or maybe something you'll remember, is we have a way of testing if a graph is a function using what's called the vertical line test. And what that is just a way of checking to make sure that every single input has only one output. If I think of vertical lines going through this graph, I could look for the number of times that these vertical lines intersect my graph. If they only intersect once, what that means is that I only have one output for every one input. So like you could think of it as thinking that this x value, where this vertical line is, this x value has one output here, this x value here has one output here. That's the vertical line test. And you might see an equation, something like f of x equals 2x plus 3. We call this function notation, this whole f of x thing, and usually it's a good sign that if you see f of x, that kind of guarantees you that it's a function since it's a function notation. So that's all well and good. What are some things that are not functions? Well, I could take the same type of idea that I had before with a map, 0, 1, 2, and let's this time map to I don't know, 5, 8, -1, and 6. And so what I could say is this would not be a function if 0 could map to, let's say, 5, 1 might map to 6, but let's say 1 also maps to -1, and 2 maps to 8. The reason why this is not a function is because this input of 1 in my map maps or points to two different outputs. And that's not an okay thing. Every input should only map to one output, so that doesn't work. Not a function, I could say 0, 1, 1, 2, and I could do the same thing with my map. This could point to 5, or output or input of 1 could have an output of 8 or -1, and then output of 2 could, let's say, have 6 or something like that. This is not a function because I've got repeated inputs that yield different outputs. What's an example of a graph that's not a function? Well, probably a very easy example is a circle. This does not pass the vertical line test. This is something that if I were to take a look at an input x, I have two different places or I have outputs, so this is not a function, fails the vertical line test. An equation, you are not going to see f of x when we're not talking about functions. One example of an equation that might not be a function could be the circle, x squared plus y squared equals 25, or here's another example of something that's not a function. We could say x equals y squared. And if you're not sure what that looks like, I encourage you to graph it and see what it looks like. Maybe use Desmos and see what this picture looks like, and you will see it does not pass the vertical line test. All right, so those are examples of what functions are and what functions aren't. So let's evaluate functions using function notation. Here I'm given a function g of x. It has a name called g. I have an input. Maybe I'll actually write that down. G is my name. We're going to name it g. I have an input. Input. And this means that I input x into my function called g, and then this whole other thing yields my output, or it's my rule. The rule of the function. The output is what I get after evaluating whatever my input is. So let's do that. Let's find what g of negative 2 is. So this is going to be g of negative 2, means I just take negative 2 and I plug it in for my x values. So 2 times negative 2 squared minus 2, or rather minus negative 2. And now I just evaluate. So this is going to equal 2 times 4 plus 2, or 8 plus 2, or equal to 10. Done. So g of negative 2 is equal to 10. Actually, I should probably write the full function notation statement. G of negative 2 equals 10. There we go. All right, next example, g of x plus 3. Notice this time I'm not plugging in an actual value, but I'm plugging in an expression. That's an okay thing to do. G of negative 2, let's switch colors here, or g of x plus 3, rather, means that I'm just going to take x plus 3 and put it in for my rule, or put it in for my input in my rule. So this is going to be 2 times x plus 3 squared minus x plus 3. This will equal 2 times, I got to expand x plus 3, x plus 3, oops, x plus 3 times x plus 3. Remember, this is not x squared plus 9. Don't do that. Don't ever do that. I'm multiplying both of these things together. Minus x plus 3. All right, so it's going to equal 2 times. We can multiply these two to give me x squared plus 6x plus 9 minus x plus 3. I will distribute that 2 through, 2x squared plus 12x plus 18. And then let's distribute that negative, minus x minus 3. Let's combine all of our like terms here, and we get g of x plus 3 equals 2x squared plus 11x plus 15, and that's it. So this time I'm actually given like a new function when I evaluate x plus 3 as my input. So we can call this g of x plus 3. All right, last example here. Let's plug in 1/2 b squared, and let's go purple for this guy. So same process here. G of 1/2 b squared means that I'm going to plug in 1/2 b squared. Oh, running out of room here. Let's do this. Let's make it all one line. So this will equal 2 times 1/2 b squared squared minus 1/2 b squared. So let's evaluate. This is 2 times, I'm going to square this, so this is going to be 1/4 b to the 4th, wow, minus 1/2 b squared. Or this is going to equal 2 times 1/4 is 1/2 b to the 4th minus 1/2 b squared. And that is what g of 1/2 b squared is equal to. So just like that, plugging in inputs, evaluating, simplifying, sometimes you get numbers, sometimes you get expressions. But notice, I can put all kinds of things in for this function. I could put in numbers, I could put in other x values, or I could put in even other variables or symbols. So why don't you try an example. Oop, there's the answer. Why don't you pause the video and give these problems a shot, and then you can look at these answers and see how you did.